Okay, right, hi everyone. Thank you for that. I'm going to talk about similar kind of area, but life cycle thinking, life cycle assessment. Try to use that as a concept in this area with an example from a project that we finished fairly recently. This is going to work. So, so biological resource use is obviously very, very broad. There's a huge amount of things we can do with biological resources. And I don't know about you, but I typically go straight to energy as the more successful area so far in terms of how we use biological resources. So I'm sure you're familiar with most of this stuff. There is a sector in which bio things are quite well established. So, for example, we have direct combustion basic power, that's already very well established. Things like you may be aware of DRAX, the formerly coal-fired power plant in Yorkshire, which is now the biggest consumer of wood pellets on the planet. It's converted about half its capacity to biomass firing. So that kind of thing is very well established. There's lots of CHP, Chinese power plants, are enough biological waste resources and that kind of thing. Anaerobic digestion also quite well established. Lots of places where you have access to quite liquid biomass feedstocks, maybe slurries and manures, that kind of things for farms, in which case you can produce methane from anaerobic digestion. Gasification, you can gasify lots of different types of biomass as well to produce syngas, a mixture of hydrogen and carbon monoxide. Less well established, but at least the principle is very well established. And I'm sure you're all familiar with first and second gen liquid biofuels as well, so the kind of things that we will already come across, like bioethanol, biodiesel, lots and lots of different production routes for those things, which are quite fairly receiving an awful lot of investigation at the moment. The characteristics of those, of course, are the first gen, you're probably familiar, there are quite a few potential problems with that. So that's mainly fuel made from starches and sugars. One problem being that you're necessarily competing with food production. If you do that, you're normally using crops made specifically to produce fuel, so that's one in itself, economically and socially. So second generation, the move there, the rationale behind that is mostly to do things like using waste products to try and avoid competition with food. Lots and lots of different pathways you can use there, so I don't think we need to go into all of those there. But, just to give that as an example of the fact that biological resource use in energy is quite successful, quite prolific, and lots of research going on in there. But there are quite a few questions that we should ask from that. For example, if our goal then is to try and try and replace fossil fuel derived things in general, then what about chemicals and materials? So, okay, we can replace all energy with biomass based products, but what about chemicals? Of course, most of the things we use in daily life contain petrochemicals, whether it's shampoos or cosmetic products or food products, sorts of things. Materials, the vast majority of plastics, of course, which is used in pretty much everything, are petrochemicals. So what about replacing some of that as well? To what extent is that possible? Other question might be, does bio actually mean sustainable? I think we are mostly guilty of falling into this assumption that if the word has the bio prefix at the front of it, it is green. Is that actually the case? Are we sure that it is? And I think that's quite important actually, because the more that if we're not careful, if we put across new concepts that we claim to be green, and then we later find out that they're not as green as we thought, then the danger is that we kind of disenfranchise lots of people from the whole idea of being environmentally friendly in general. So we have to be quite careful and quite robust, I think, in making sure that what we're doing is actually sustainable. And what does sustainable even mean? Because it's one of those words that is thrown around a lot without much clarity sometimes. So, sustainable development, I'm sure you've heard this 1,000 times. So this is the generally accepted definition of things that are sustainable. We're talking about development that meets the needs of the present without compromising the ability of future generations to do that themselves. So that's all sort of nice, we can all get behind that idea, but it's a bit difficult to work with what does it actually mean. So normally we talk about it in terms of these three dimensions. It's trying to make some kind of rational, reasonable compromise between impacts on society, economic viability, and environmental impacts as well. So that's what we're trying to aim for here. The problem with that is that it throws up a whole pile of issues, because ideally we don't want to come up with something that is beneficial to one of these three areas, but causes significant detriment to others. Similarly, we don't want to come up with an idea that is, let's say, socially beneficial in the part of the life cycle that we're looking at, but then causes all sorts of social problems elsewhere. Similarly for economic problems and environmental ones as well. So, in order to try and approach these things robustly, one of the things that we try to encourage is this idea of life cycle thinking. You may be familiar with this stuff already, so I'm just going to run through it quite quickly. Typically, when we are looking at developing new processes or products, we look at the bits that are kind of obvious, the bits that we're actually working on. So that could be the production process itself, if we're developing that, or it could be we're consumers, then we probably look at the bits that we see in the shops. You're going to buy a product or a service, and then using that product or service and eventually some kind of disposal. We don't really think about the other stuff that happens. Of course, behind the scenes, there's all sorts of stuff happening. So it's not just the process that we're developing or the product that we're buying, but in the background you're having lots of different resources being extracted from all over the world. You are having to transport those resources to various different processing steps, more transport to consumers, more transport to waste, to some kind of recycling and recovery processes, and ultimately to final disposal as well. And all of these things have consumption resources, economic costs, social impacts. Could be things like negative health impacts, for example. But on the plus side, they also provide benefits like services and employment, that kind of thing. Economic benefits, obviously, and sometimes positive environmental impact as well. So, what we're trying to do is to take account of all of this by the idea of life cycle thinking. Now, that's partly established in certain areas, but not well established in others. So, when we think about the environmental part of those three areas I talked about before, LCA, life cycle assessment, is very well established. This is the kind of thing that we can use during process development and assessment. So that involves quantification of environmental burdens, so that's emissions to the environment really, use of energy, use of materials as well. Quantification of the impacts of that, so trying to translate those burdens into impacts, because of course if you say, okay, we have a direct emission of such and such a chemical here, that's not necessarily helpful. You have to kind of translate that into an actual environmental impact that we can have a look at. And one of the most useful parts is to identify opportunities where we can improve things. That's particularly important when we're developing new processes. If you can do some kind of rough life cycle assessment, you may be able to point me in the direction of making major improvements by saying most of our impact is coming from this particular bit, so let's see if we can improve that a little bit and build life cycle assessment into the development process. You can also use this to compare different alternative products and different scenarios, that kind of thing as well. So as I say, life cycle assessment of the environmental stuff is pretty well established. It has its own ISO standard, which broadly looks like this. We don't need to worry too much about all these bits and pieces, but you can see there are 4 stages. Basically, the first one is to define what you're actually going to study. The second one is to collect lots of data, so that's mostly things like the resources you're using, the energy consumption, direct emissions, that kind of thing. I'm sure you can imagine that when you're trying to model something like this, as I said, it's a big life cycle of things happening all over the world, it's kind of impossible to do the entire thing yourself with a huge data requirement. Luckily, this has been going on for quite a long time already, so there are databases that exist. So, for example, if you are developing something that requires a steel vessel weighing 100 kilograms, there's already been life cycle assessments of steel manufacture with various different conditions and steel working and that kind of thing. So if we know that's what we require, we can plug that LCA data in to this data collection section to help us model the final product. And then you've got the impact assessment, which is where we try and turn these resource uses and emissions into environmental impacts that we're familiar with, like global warming, that kind of thing. And then the final bit is basically run this iteratively, have a look at the results, see if you can improve any bits, see if you satisfy your aims from the start. So that's all I'm going to say on how LCA actually works, but of course I'm going to answer more questions about it. I thought I'd move on to a bit of an example within this area to give you an idea. So this is a project that we completed towards the end of 2015. It's looking at using lignin as a resource for industrial chemicals. sure you're all familiar with lignin. It's about 25% of the mass of plant cell walls. It's very difficult to use. It's a structural component, so it's very difficult to degrade, quite tough. But there is a lot of it. There's lots of ways of using lignin, and we don't really harvest it very well at the moment. We don't really harvest it at all. So it's quite a good resource there. So this project was called Bio-mimetic. It was an EU-7 framework project that finished towards the end of 2015. And the aim was to develop and test production methods and use cases that polymers created from renewable feedstocks. The emphasis, as I say, was on lignin, because firstly it's one of the most organic, one of the most abundant organic polymer on Earth. It's also the most abundant phenolic polymer. As I'm sure you know, phenolic compounds tend to be quite useful oil chemicals in all B1 groups. So we can harness that and do something useful with it, and it's potentially a great resource. So you can extract lignin from basically any kind of woody biomass because it's the structural component, so it's in generally. This part of the study was by a project partner called CINP in France. So they developed an organic solvent process. Imagine something called organic solvent, which is now more or less a commercial scale. So you use that to extract the lignin. As I say, potentially you can use this on anything. We were looking at wheat straw and corn stover because they were quite readily available in the geographical area, and also they came up with lignins that have quite these characteristics that we use with the next stages. So that's where we're getting our lignin from. So as I say, we're trying to use waste products instead of competing with food. And this is the overall system boundary. So in life cycle assessment, we try to be quite careful to draw this system boundary so it's clear exactly what we're including and what we're not. And this is the whole sort of value chain, if you like. So at the start, we get the corn stover cultivation and harvesting. We then extract the lignin from it with that organic solvent process. And then we functionalize that lignin with an enzymatic process, carboxylation via enzymes. So we have to include producing those enzymes as well, and producing the molecules that we're using to functionalize our lignin. Then you've got the use of the biopolymer in any product. So you would remember this reason we can then use, in this case, in multi-detergent products. So the project team was led by E&G, so they were both leading solutions and products. So that's the general overall system boundary that we're looking at here. So if I can give you a bit of an example of what you come out with actually doing an LCA. So if we look at just the first section for a starting point, getting the corn stover, extracting it, transporting it, getting the lignin from it. This is our first part of the assessment. So we ran a life cycle assessment on that, collected all the data on the energy, resource use, the chemical use, etc. And this is what we came out with. So you can have a look at various different environmental impacts here. These will vary depending on kind of methodology that you use. I'll point you to a few. GWP is global warming potential, the one on the carbon footprint, so I'm sure you're all familiar with that. All these other things are kind of similar, so you're probably aware that the carbon footprint, the idea is that there are lots of different greenhouse gases with different impacts on global warming. And the idea is that you're trying to make them all equivalent to carbon dioxide. So methane, for example, is roughly 30 times as potent over 100 years as CO2. So if you have an emission of methane, you basically just multiply it by 30, and that makes it equivalent to CO2. So then you can remember the carbon footprint, which is expressed in carbon dioxide equivalent per whatever your unit of assessment is. These other impacts do the same thing, but for emissions that cause different types of environmental impact. So here's acidification potential. You're probably familiar with acid rain and acidification of water, that kind of thing. Eutrophication potential. Freshwater aquatic ecotoxicity potential, so that's emissions of things like heavy metals and other toxic compounds in freshwater. Over here you've got the same things in marine areas. You've got human toxicity, ozone layer depletion, photochemical oxygen creation, so that's photochemical smog, the kind of smog you get in industrial areas from emissions from transport and fossil fuel combustion. Terrestrial ecotoxicity potential, and over here we have depletion of resources as well, so depletion of elements and depletion of fossil fuels. So you run the LCA, you build your model, and basically press go, and this is the kind of thing that comes out. So you can then see where your hotspots lie, which bit causes the biggest impact, and that can be quite useful. In this case we can see that generally speaking, the impacts come from steam and from chemicals that you use. So that immediately gives you a starting point. If you could recycle a few of those chemicals perhaps, then you immediately get a big savings. If you can produce some of your steam from bioresources instead of natural gas, you will probably get some pretty good savings there as well. If you can do some heat integration to reduce your steam requirement, that kind of thing. So it gives you a few starting points of how to make the process more environmentally friendly. Conversely, it would also point in the direction of saying, okay, there are certain bits here where we don't really need to make too much effort, like the solar process itself, the direct emissions from it don't really cause any significant impacts on the life cycle, so let's focus on some of the bits instead. So that's the kind of way that you use LCA when you're doing these kind of new processes. A few things to think about in terms of general biological processes like this, problems that will crop up in lots of different scenarios, not just in this particular project, but others. Biological processes tend to have a lot of multi-output systems. So to take our example here, we would take a biomass and get a lignin. But of course, biomass contains lots of other stuff as well. Cellulose, hemicellulose, it contains various non-sugars, it contains different types of silica depending on the feedstock as well. So you've got lots of things coming out of the process. And what you do with those things can then affect the sustainability of the process as well. So one of the nice things about this is that we can run lots of different scenarios to explore what if we use this byproduct for this, or use it for this instead, and we can see what happens. So in this case, we were able to show that the version of this process with the lowest carbon footprint was where you're using the spare cellulose, you're selling that as paper pulp, and you're converting the heavy cellulose to ethanol. The silicon is not what you can do with just silicon, but there are various different things you can do with these little bits. So the non-sugars we explored as well, potentially you can use some of those for cathode feed and kind of things. There's different scenarios of things you can do with byproducts, and this allows you to explore those options and see what the most sustainable is. Other questions that are thrown up by this project and apply to pretty much all similar projects. Is waste actually waste? So I've said that we want to generally use waste rather than things that compete with food, but quite often things that we think of as waste aren't really, but do have some kind of function. So if you're using something like this, we talked about extracting cornstalk in some crop field. If we take that away, there are consequences. If we take all of it, you could have some soil erosion. Typically that would just be left on the field, and if that happens, then it's providing nutrients back into the soil. So if we take it, we need to add more nutrients back into the soil. So it's kind of a waste, but you're having to add more fertilizers if you use it. If you were to burn it to provide heat and then land farm the ash, then it's providing energy and it's providing nutrients back into the soil, which no longer happen if you take it. If you use it as animal feed, then it displays other animal foods. So you have to try and be as comprehensive as you can and think about the actual impact of extracting this stuff, because quite often wastes are not 100% useless. So to make a fair assessment, we have to account for this. So we did. It means it's a bit more complicated to model, but it's going to do it. Other things to think about are the functional unit that you use. So this is a term that we use on the unit of assessment. So you build your model, and you might model something based on a kilogram of products, for example. We have to think about whether that's reasonable or not. So in this case, if we look at the half-skip stage here, I've gone from the lignin extraction through the enzymatic carboxylation stage to the product itself, so we'll skip that middle section. But once we had this more or less complete model, we were looking at it per kilogram of model of product. And this was carboxylated lignin, the idea being to replace polycarboxylates in detergents. So we thought, okay, let's compare a kilogram of our product to a kilogram of polycarboxylates. And we did that, and it all looked a little bit scary because our product was worse than the conventional polycarboxylates. But then luckily, there was some lab work done which found that actually it's more effective than conventional polycarboxylates. So this was a very lucky coincidence that meant that we would use 20 times less oil. And so that's pretty much all I was going to talk about really. I guess the outcome I would say from this is that it does seem to suggest that lignin is quite a promising feedstock. There's so much of it, and there are things that you can do with it that appear to be fairly environmentally sound. This only focuses on one enzyme group, on one type of functionalization. You can do all sorts of good stuff as well, so there's a lot of ongoing work there. But what we can learn from this in terms of bioprocesses in general we do need to consider the whole life cycle, including the knock-on effects of things like using waste products as well. Otherwise, it's not really going to be fair. And we do need to also consider those bits that are not talked about, like social impacts, effects on employment and health and that kind of thing, rural communities potentially, economic impacts, all this stuff needs to be looked at as well, to get a sense of whether we're actually doing something that's genuinely positive or has a load of sort of knock-on detriment that we've got out of that. So I think that is pretty much everything. Thank you very much.